Hey everybody, today's video is about areas between curves. So this is the last chapter of calculus, and just as you'd suspect, we've only done essentially three different topics: limits, derivatives, and antiderivatives. And the last piece, or the last chapter we have to study is what are the applications, what are the word problems, what are the real applications, where do we use integration in real life? And that's the last chapter of calculus. So we're almost done, last chapter. So different kind of notes. I'm going to read this with you guys. It says area is always positive. Up until now, we've only considered area between a curve and the x-axis. So every time we take the integral, remember we used to always take, essentially, if I drew any graph, when I took the integral, remember I made little rectangles? And I tried to make as limited as made, infinite as many rectangles underneath this curve. That's how I found the integral. But the problem is, what if we wanted to do it for a region, or what if we wanted to do it between two curves? And some of you are saying, like, who cares, and why does it matter? And there are applications for it, and we'll go over that later on. How do you do it? And this note says to repeat it several times, and maybe it'll help you memorize it. But it's always just top minus bottom, right minus left. Top minus bottom, or right minus left. So I was telling you, we've been approximating areas by rectangle approximation. So we've been doing, even though it's the antiderivative, remember the antiderivative represents just infinite rectangles underneath a curve. Now, what it might look like if I have two curves is if you can look at this graph right here. What if I had one that was up here, one down here, and I wanted to get the area between them? Well, technically what I'm doing is finding the rectangles under this curve, and then the rectangles above this curve, and I'm sort of adding the two of them. So if you think of it as rectangles in the past just between the curve and the x-axis, now we're thinking about rectangles all the way across between two curves like so. To find the integral between, or find the area between two curves, and you can sort of tell where this is applicable, shapes that are not squares or triangles or circles. Like what if I wanted the area of a pond, and I had like these curves? I could use the integral between the two curves and apply this formula. And as I was telling you, what you need to remember is just top minus bottom, or right minus left. So all it is, I'm just boxing and highlighting different parts of the notes, top minus bottom. So all I have to do is find, where does the curve start and end? So that's where I get a and b. I take the function which is on top, which in this case is f, and subtract the one on the bottom, which in this case is g. And some of you are saying, like, where did that if I go back up in the notes, where did this right minus left come from? Sometimes, and we'll go over some examples, some people want curves or rectangles going in this direction. But in our case, or just for this video, all we care about is these, they call vertical rectangles, which we've been doing pretty much all semester. So let's look at an example, okay? And this one, and in this case, at least by now, we need to get very familiar with your graphing calculator. Again, you cannot pass the AP exam with a graphing calculator. So example 1 says, find the area of the region bounded by e to the x, and vertical lines 0 and 1. 0 and 1, these vertical lines, tell us where the bounds are, where to stop and begin. Because if you don't tell us, then it'll just go on forever. Okay? And here are my two curves. Now, how do I know which one's on top and which one's on the bottom? I mean, you could make a table, you could do that, but if you have a computer, you have a calculator, there's no point of making a table and doing stuff like that. You want the machine to do the work, the hard work for you. I opened up, this is a graphing calculator called Desmos, and let me just graph e to the x. I'm not sure I could squeeze this into the camera. Yeah. Sorry, give me just a couple seconds. All right, there you go. So here's my graphing calculator. This is for a different problem, but I want to know, looking back at our notes, e to the x and x, which one's on top and which on the bottom. So you can put it into your graphing calculator. In this case, I'm using the internet because I don't have a graphing calculator that I could put on the screen for you guys. So I'll graph e to the x. So that blue line is e to the x. And I will graph x. Oops, let me just do y equals x. So here, the blue represents e to the x, and the green represents y equals x. Now tell me which one is on top, from 0 to 1. So if I look just from 0 to 1, remember that's what the problem said, I'm just going to zoom in real quick. So only from 0 to 1, you can see that clearly the blue line is way more on top than the green one, or e to the x is above x. So when I go back to my problem, what I'm going to do is I'm going to write the integral. It already gave me bounds 0 and 1. We proved that e to the x is on top, so e to the x goes here, and I subtract the 1 on the bottom, minus x. If you have a calculator, now's the time to be able to just put this in a calculator and figure out what it is. I think you'll get 1 point something. Okay. You should also know, just in case, I mean, for these problems, they don't expect you to do it by hand because finding out the formula is a lot of work anyway. But just in case you want to know how to do this by hand, you know the antiderivative of e to the x is e to the x. You know the antiderivative of x is half x squared. And then I'll put my brackets because I took the antiderivative already from 0 to 1. I plug in 1, I plug in 0 and subtract the 2. If I plug in 1, I get e to the 1 minus half. If I plug in 0, I get 1 minus 0. When I subtract across, I get e minus half minus 1. I get e minus, taking this as like 1.5, e minus 3 over 2. Okay. On a calculator, I'll teach you guys in class how to do it. I use something called, it's a website called Wolfram, Wolf, R-A-M. And it's pretty cool because you could just tell it, you could just type what you want. So I already asked it, but let me type it again for you. So this is a website, it's called Wolfram Alpha. So let's say, hey person, it's not like Siri, but so what's the integral of this? What is the integral of e to the x minus x from 0 to 1? Okay, all I have to do is type it up. And then Wolfram, with its awesome computing power, writes out the definite integral. It even completes out the steps for me and tells me how much it is, 1.21828. Even has a vertical representation, or visual representation, all these different things. Wolfram Alpha, pretty cool. Also an app on your iPhone or iPod Touch. So the answer is about 1.2. Okay. Oops. Let's go down to example number 2, and it says find the area of the region enclosed by x squared and 2x minus 2. And you notice in this problem I'm missing the bounds. So what they're trying to get you to do is look at the graph and figure out on your own where are the bounds. So I'll go back into my graphing calculator. Also I need to know which one's on top and which one's on the bottom. So the first one says y equals x squared, so I'll type that. The second one says 2x minus x squared, so I'll type that. And now, again, this one is in blue, this one is in green. If I look at it, you'll see that they're bounded, like where it's trapped. You see from 0 to 1. That's where I get this nice, not really nice, but this weird round shape from 0 to 1 that is bounded by green and blue. Right here, this space right here. Okay, so I know my bounds are going to be from 0 and on the x-coordinate to 1. Those are going to be my bounds. And I know that green, or 2x minus x squared, is on top, and I know that x squared is on the bottom. So I'll go back into my notes from this new knowledge from my graphing calculator. You know that my bounds are from 0 to 1. Oh sorry, I coughed. You know that 2x minus x squared is on top, and minus the one on the bottom, minus x squared. Again, this is something that you should be able to do on a graphing calculator because it's a lot of work, especially for an AP exam. If you want to do it the manual way, it would look like so, right? X squared and x squared is minus 2x squared. You'll notice that I have a 2 in both of them, so I could factor out that 2. I could take I don't need u substitution. I know the antiderivative of both of these. Antiderivative of x is half x squared, and antiderivative of minus x squared is 1/3 x to the third, 1 and 0. I will then plug in 1 and plug in 0 and see what I get. So remember that 2 is still on the outside. If I plug in 1, I get half minus 1/3. If I plug in 0, I get 0 minus 0. So all I get is a half minus 1/3. Just doing common denominators, 3 over 6, 2 over 6, just 1/6, which I get 1/3. So again, this is something that you could do in your calculator. All I'm going to do is, or you could use Wolfram Alpha, 2x minus 2x squared. Like say for example, I wanted to put this in the graphing calculator. Let me use Wolfram again because he's awesome or she's awesome. 2x minus 2x squared. What is the integral of 2x minus 2x squared from 0 to 1? So it looks exactly like it, and they also get 1/3. Give me a good picture. So pretty cool that this I want to say an app, but this website can understand regular English and give you the correct answer. And some of you hopefully are amazed by it because technology has come a long way. What we're going to do is we're going to skip number 3. This one says how to use your calculator, and we're not going to do that. Okay. Skipping over to number 4. We did an example like that, so we're going to skip over number 4. And we'll get to that in class. And the last one I want to do is, this one says the vertical slicing method. And example 6 says use the horizontal slicing method. Some of you are saying, like, what the heck does that mean? Okay. Vertical slicing method is everything that we've done so far, up and down rectangles. Okay. And it wants to do it between radical x, y equals 0, and x minus 2. And just as you can suspect, I need to put this in a graphing calculator. This y equals 0, remember every time they give you a point or just like a number, that tells you where one of the bounds is. Okay. So let me write this out. Radical x, which is the same thing as x to the half. Okay. We also wanted y equals 0, so let's type in 0 so you guys can visualize it. Oops. Y equals 0. So let's see that green line down there. And y equals x minus 2. So on a graphing calculator, there's the picture of that. So here's the green, here's the blue, here's the purple. And you'll notice, if I zoom out real quick, my bounds is this weird sort of, almost like a wing of an airplane. And you can sort of tell, like, you know, this is probably where they apply it because it looks like some of the geometric shapes we see in architecture or airplanes and stuff like that. But do you see this green, purple, blue boundary? Using vertical rectangles, I'm going from 0 all the way to 4. That's where this bound closes. So I'm going from 0 to 4. And x, square root of x is obviously on top. Okay. So when I go back, I'm not going to solve this all the way, but I'm going to want the integral from 0 to 4, radical x, minus, and I'm subtracting this x minus 2. And this is where you need to be careful. So you have a minus x minus 2. This minus has to distribute. So if you're going to put it into a calculator or Wolfram, I'm going to have to put 0 to 4 radical x minus x plus 2. And you can put this in Wolfram Alpha. You can do this manually. Totally suggest using a calculator because it's a lot more easier. How about that? Or a lot easier. I'm not going to solve it all the way through. But example 6 says using a horizontal slicing method. Horizontal meaning, remember when I drew the picture, instead of doing a rectangles like so, what I'm going to do instead is rectangles that go horizontally. Okay. I'm trying to delete this. There you go. Exact same functions that we're looking at, radical x, 0, and x minus 2. When I look at my graph, now instead, you have to use your imagination here or turn your head with me here. But I'm going to do, essentially instead of going from x equals 0, from x to 4, I want to do it on the y-axis, from smallest to largest. Okay. So see here, it bounds from the y, it goes from 0 all the way to 2. Okay. So if you understand for me that it's bounded on the x-axis from 0 to 4, hopefully you understand with me that this is bounded from 0 to 2, going from down to up. Okay, from down to up. And now, what I'm going to do is, which one is most right minus the left? Do you agree that this purple one is the rightmost compared to the blue on the left? You're going to imagine we're making rectangles. I know I'm tracing this with like a yellow pointer, but I'm making rectangles like so. So that's why if I tilt my head like to the right, so if you tilt your head to the right like so, it looks like purple is technically like top and blue is on the bottom. Or if your head is tilted regularly, this is the right and this is the left. So what you're going to do is you're going to subtract this one minus this one, and my bounds, instead of going horizontally from 0 to 4, I'm going vertically from 0 to 2. So what it looks like is from 0 to 2, of the one that's the rightmost, which is x minus 2, minus radical x. So if you look at, again, if you look at it this way, that's how, that's sort of, that's how I get that. Okay. So that is how we do the different types of slicing methods. This is how we find areas between curves. We will do a lot more practice in class. Hopefully you guys understand it. Hopefully you guys bring your graphing calculators. I know some of you don't have graphing calculators. I don't want to make you guys do it, but I'm pretty sure, or I'm positive that you will be more successful if you have one. Thanks for watching this video. I'm going to answer the questions, and I'll see y'all tomorrow.